All right, as people are coming in, so that we start on time, we are going to welcome you. Welcome to the session on Trustworthy AI. There will be an announcement in the chat about making sure that you use the Slack channel to do the questions. I'm Amy McGovern. I'm one of your two co-chairs. And Julie?
I'm Julie Demuth. I'm the other co-chair.
And Antonios, if you want to start sharing, yes, it has been a day, sharing your screen. We will start right when it says 15 after.
So should I go ahead or, yeah.
Give it 30 seconds because we are still at 3:14 and I'm trying to get till 3:15
okay.
And because there's still people in the waiting room.
Okay.
All right, I think now we just crossed. I didn't know it was like 2 seconds before. So yes, go ahead and I will cut in at 10 minutes.
Okay, thank you, Amy, for the kind introduction. Welcome, everyone. Thank you for being here. I would like to thank also the organizers for the opportunity giving me to talk about my work. I also want to acknowledge the contribution of my co-authors to this work, Ima Ebert-Abhoff and Elizabeth Barnes from the Colorado State University. Today, I will be talking about the need for objectivity, for introducing objectivity into assessing methods of explainable artificial intelligence. So, for those who are not very familiar with what explainable artificial intelligence or XAI is, think about the typical prediction setting that we are interested in predicting a variable y given a variable or multiple variables x, and we want to do that using a neural network. Now, in our field, it is very important to be able to, apart from achieving a high prediction performance, it is very important to assess physically also what the model is doing. And the neural network being a black box doesn't allow for this. And so XAI is this new emerging field of methods that aim to posteriori explain what is the decision strategy of the neural network. And this brings many opportunities for us as scientists to apply these methods in our field. First of all, as I said, it is assisting us to physically interpret the model and increase trust in the model architecture and what the model is doing. Second, for models that do not perform that well, we can gain insight as to what is going on and why. And so we can improve, refine the model architecture and refine and improve the prediction performance. And third, which is also very exciting, these methods, especially when we apply these methods in problems where are relatively new to the field and we don't have so much scientific insight, these methods can help us gain insight into relationship between specific predictors and the output, and so accelerate exploring further new mechanisms and connections that help us learn new science. Now, despite all these promising and very, very highly beneficial things about and opportunities that XAI is bringing, I will push back a little bit here and say that we need to be cautious about how we implement these methods. And specifically that we need to introduce objectivity in assessing these methods. What you're looking at here is an example of published in by computer scientists. And here the authors have trained the convolutional neural network to classify different pictures and then use different XAI methods to be able to gain insight as to what features were important for this specific classification task. Now, it is very cool to see actually in the heat maps here what features were important for this classification, but there are two main issues. First of all, there is no ground truth as to what the explanation should look like. So even if we say, okay, it makes sense that the network is looking at the eye of the bird as some methods show here, or at the edge of the body of the bird, or at the belly of the bird, the fact that it makes sense doesn't mean necessarily that this is what the network is doing. The second thing is that there are so many different XAI methods in the literature, And believe me, there are many more than what it's shown here. So, and although this is the same model, all these methods are applied in the same model, they aim to explain the same model, they provide different answers in terms of the explanation. And so there is some uncertainty as to what actually the model is doing. And this uncertainty propagates into limiting, in a way, the trust that we were aiming at building with applying these methods. So there is a need to come up with objective frameworks to assess these methods. And I will be offering here in this talk today a way to do that. And this way is based on constructing benchmark data sets where we know the connection between X and Y. And so we can objectively assess how well these methods are doing. And this data set here is inspired by a climate prediction setting. So the first thing to do is to essentially create a synthetic input, which consists of a sequence of fields, of random fields generated from a multivariate normal distributions with some specific spatial structure. And this, let's say, aims to represent sea surface temperature anomalies. Then each field of these SST anomalies is passed through a nonlinear function and gives us an output, a scalar value of Y. Now, this function F, this nonlinear function F, I don't have too much time to go through the details here, but one can say is essentially a weighted sum of the input values. And this weighting is depending on the input. So it's highly nonlinear function. Things get more interesting in step 3, where we pretend we don't know this function F that we used to create the values of Y. Of course, obviously, we do know this function F. We pretend we don't know it, and we train a neural network to approximate this function and be able to predict the value of Y given X. And because this is a synthetic data set, we can create as many samples as we want. I have created here 1 million of samples. And this can help us achieve a very high prediction performance and essentially assume that the network has very closely approximated this function F. And then, since we know the function F, we can derive the ground truth of how the explanation should look like and compare that ground truth to what the XAI methods give. And that's the whole concept. This is an objective way to assess these methods. Let's see an example. Here, this example that I'm showing, the Y value is 0.066. The prediction is quite close. And what you're looking at here on the top is the ground truth of this explanation of the attribution. So pixels here that are illustrated with a red color positively contributed to the value of Y. And pixels that are illustrated with a blue color negatively contributed to the value of Y. And we know that because we know the function F that we use to create all this data set. Now, let's see what the XAI methods give. As you can see, first of all, big uncertainty as to different methods provide different answers. And so if we didn't know the ground truth here, I don't think we would be able to be confident about what the model is doing, what this neural network that we have trained is doing. And this can be very problematic, especially in problems that we don't know, we don't have big scientific insight. Just although the details of these methods are not the point of this slide, I will briefly mention that we can easily spot that the first two methods, gradient and smooth gradient, do not provide consistent contributions. We can easily spot that the method Deep Taylor and LRP alpha 1 and beta 0 highlight everything as positively contributing to the prediction, which is clearly not the case as assessed by the ground truth. So we need to keep that in mind, that these two methods possibly mix positive and negative contributions. And the last three methods are quite similar, and they provide the most consistent attributions in this case. But the point of this slide, apart from assessing individual methods, is that this is an objective way to gain insights about systematic weaknesses and strengths of different methods. And to conclude, the key take-home message here is that there are many XAI methods in the literature, around 30 or 40, I don't know. And each one is aiming to explain the network in a different way. And that's fine, but we need to know the relative weaknesses and strengths of each method. And there is no ground truth so far in the literature as to how objectively assess these methods. And so in this talk, we introduced the concept of attribution benchmarks, which are datasets, synthetic datasets that consist of synthetic input and synthetic output, and can have an answer, a ground truth, can provide a ground truth as to what the explanation should look like. All these results and many, many more details have been posted in a paper into archive. So all these are available online. And so with that—
You're at your 10 minutes, but you're perfect on timing. Look at you.
With that, thank you. With that, I will conclude. I'm happy to take questions. And also ping me, please, ask me in Slack. I believe it's channel 9. So I would be happy to—
Yes, it's channel 9. And please, anybody ask a question, he's got about a minute and a half in which to answer a question before we switch to the next talk. And the next speaker can go ahead and change to their slides. You do have a question in the chat. When talking about benchmarking, how challenging will it be to develop it for Earth system studies?
Oh, yeah. I mean, this dataset that we have created is inspired by climate prediction setting, as I said. And I think it can be quite challenging, but this first dataset is for regression problems, and I think it's quite robust. The insights that we gain are quite robust. I don't know in general how— I cannot think of very accurately answering this in general.
You can answer in more detail in the Slack.
Yeah, I cannot. Yeah, that's true. Yeah.
Perfect. Wonderful. Thank you, Antonio. So I think we'll go ahead. We're kind of right on time here. I'll remind everybody that we're using Slack channel number 9, and we're going to move on to David Harrison, who's going to be talking about developing machine learning for an operational environment. So take it away, David.
All right. Hello, everyone. My name is David Harrison. I am a research associate at the University of Oklahoma's Cooperative Institute for Mesoscale Meteorological Studies and the National Weather Service's Storm Prediction Center. As a researcher at the Storm Prediction Center, a lot of my work focuses on machine learning and how it can be used to help forecasters in operational environments. Now, machine learning, deep learning, and other artificial intelligence methods have recently become very popular tools within the meteorological research community. And there is, in fact, a large breadth of research that suggests that artificial intelligence could become a valuable tool within operational environments. However, at this time, artificial intelligence techniques have yet to become widely utilized within the operational community. Now, there are multiple studies and collaborations currently ongoing to investigate the different human and technological factors that might influence whether and how artificial intelligence methods are integrated into the operational workflow. And along those lines, the points, the research I'm going to present here today try to focus on are the questions of how does the operational community perceive AI-driven products? What are the challenges to implementing those products within an operational environment? And what can we as developers and researchers do to better tailor artificial intelligence for the operational community? Now, to help answer some of these questions, a survey was presented to participants of the 2021 NOAA's Hazardous Weather Testbed Spring Forecasting Experiment. Now, Spring Forecasting Experiment is an annual experiment hosted by NOAA's Storm Prediction Center and the National Severe Storms Laboratory, where participants investigate a variety of numeric weather prediction models, outputs, et cetera, in order to test their usability for the prediction of hazardous convective weather. Now, normally the Spring Forecast Experiment is held at the National Weather Center in Norman, Oklahoma. However, because of the ongoing pandemic, we were forced to hold this year's experiment virtually via Google Meet. And one of the benefits to having a virtual experiment is we were no longer constrained by how many people we can cram into this small room at the Weather Center. And so we were actually able to invite and receive 133 participants across 5 weeks. And this included a very diverse pool of participants from local National Weather Service forecast offices, the Environmental Modeling Center, various oceanic and atmospheric research laboratories, cooperative institutes, NCAR, members of academia, as well as members of international research and forecasting agencies. So an online survey was presented to these participants each Monday following introductions to the hazardous weather test bed. And the participants were informed up front that their participation was voluntary and that all of their responses would be kept anonymous. The survey was composed of a total of 10 questions, including 1 multiple choice, 5 matrix table questions, and 4 open response. We'll only focus on a handful of these here today in the interest of time. We are very excited to see about a 70% response rate. We actually got 92 completed responses, including responses from 36 forecasters, 38 researchers, 16 academic faculty or staff, 10 students, and 7 individuals who identified as an other category. Now, you might notice that those numbers do not, in fact, add up to 92, and that is because some of the participants identified themselves in multiple categories. The participants self-described their machine learning knowledge. Their knowledge was described as being quite varied overall. So the majority of them identified as being either somewhat knowledgeable or not very knowledgeable about machine learning techniques, with only a small handful being very knowledgeable. Notably, none of the participants claimed to be extremely knowledgeable about machine learning techniques. So the first question of the survey that we're going to talk about here today was intended to gauge how experienced the different participants were with probabilistic forecast products. For the purpose of this research, a probabilistic forecast was defined as any probabilistic guidance derived from another model or ensemble, one that perhaps represents the inherent uncertainty and spread associated with deterministic models. When we break up the responses between forecasters and researchers, unsurprisingly, forecasters were quite familiar with probabilistic guidance, utilizing it either daily or at least multiple times a week, whereas researchers' experience with probabilistic products was in fact more varied. The next question asked the participants to consider some probabilistic forecast product that they'd utilized in the past. We then provided them with a series of factors and asked them to rank how important each of those factors were when determining how useful a probabilistic product might be for their own personal forecast process. So these factors are ranked on a scale of 0 to 5, where 0 is not at all important and 5 is extremely important. And you can see the kernel density curves of the responses in this panel on the left. So we're going to start all the way down here at the bottom and work our way to the top, keep you in suspense for just a little bit longer. The least important factor, according to the survey participants, in how they evaluate a new probabilistic product was how much previous experience they have with the developers of that product. Next up the list, we have previous experience evaluating experimental versions of the product, how closely the probabilistic output aligns with human-generated forecasts, use by other experts in their field, how closely the variables used as inputs for the product align with traditional meteorological knowledge, knowledge of how the probabilistic output is derived, and performance of the product in case studies. Rounding out the top 3, we have the statistical verification of the product being the third most important factor, the timeliness and availability of the product being the second most important factor, and finally, the most important factor, according to the participants, when evaluating how useful a product is for their forecast process was knowledge of the product's limitations and possible failure conditions. All right, the next question we asked was actually very similar to that one, except this time we tell them that they are specifically evaluating a probabilistic forecast product that is the result of a machine learning model. And the purpose of this question was to try to differentiate how they evaluate more traditional probabilistic guidance in comparison to machine learning guidance. And you can see right away that there is actually very little difference in their responses. The only real differences here, the statistical verification was ranked slightly higher for machine learning guidance, and how closely the probabilistic output aligns with human-generated forecasts was ranked slightly higher this time around. So overall, participants showed very little discrimination in how they ranked these factors between machine learning guidance and other generic probabilistic guidance, with perhaps a slightly greater emphasis on model verification for machine learning guidance. Now, these results get a bit more interesting when we break them down between forecasters and researchers. So this time, the kernel density curves on the in the panel on the left here show both the answers from both groups, where the red curves are the responses from the researchers, the blue curves are the responses from the forecasters, and the dashed lines represent the mean ranked scores of for each group. And right away, you can see there's actually a fairly large difference in what the forecasters consider to be the most important factor in comparison to what the researchers consider to be the most important factor, and that is timeliness and availability of the product. Forecasters rank timeliness as the most important factor they consider when determining whether or not they want to use some new guidance, whereas the researchers rank this as about the fourth most important product. A few other differences we have are how closely the variables used as the input to the product align with traditional meteorological knowledge. Forecasters rank that quite a bit higher than the researchers. Same with use by other experts in the field, and even previous experience with the developers of the product. Although the averages are fairly similar, you can see by the curves the distribution of responses. The forecasters are actually leaning quite a bit more strongly, with this one being, maybe more of a factor than the researchers would consider it to be. So the results shown here are for the any probabilistic guidance, any generic probabilistic guidance, but the responses are actually quite similar when we consider machine learning guidance specifically. But the main difference perhaps being the differences between the researchers and the forecasters are exacerbated a little bit, with the difference on timeliness being even notably greater for machine learning guidance than it was for any probabilistic guidance. Now, we as developers spend a lot of time when we're training our models to make them as accurate as possible, to get the highest CSI scores as possible, to get the best verification, the best case studies. We spend a lot of time focusing on the verification of the product. So why in this survey do the forecasters consider timeliness to be the #1 most important factor, even over verification of the product? And well, the reality of operations is that a lot of operational products just have really strict time deadlines. The guidance that we provide them must arrive early enough for the forecasters to process our information and incorporate it into their forecast process. And any guidance that arrives after the deadline passes is just simply less useful for the forecasters. It also takes a lot of effort for forecasters to set up their procedures and to add new products to their procedures. So in order for them to be confident enough to add some new probabilistic guidance to their forecast procedure, that guidance must be reliably available and in a timely enough fashion for them to consider it worth going through the effort to add it to their procedures. All right, so after reviewing the survey results and having discussions with Storm Prediction Center management as well as Storm Prediction Center forecasters, we have come up with a series of recommendations for anyone.
David, I'm going to interrupt and let you know you're at 10 minutes, so you have about a minute.
All right, thank you. Anyone developing machine learning guidance for operational use. And although we focus primarily on machine learning, these recommendations can also be applied to more traditional products as well. So the first one is to communicate with your end users early and often. What are their operational needs? What are their technical requirements? And provide opportunities for them to collaborate with you throughout the development of the product. Program with timeliness in mind. Use good coding practices throughout your development and try to optimize the code as you go. It'll save you a lot of time than if you try to just do it all at once later on. Focus on individual cases just as much as you do bulk statistics. You need to be able to provide your end users with examples of when a product works and when it doesn't, and also be able to explain how a product works and why it might fail. Be sure to consult with domain experts when necessary and when possible. Don't try to reinvent the wheel. Any new guidance you provide should be novel or exceed the quality and skill of similar existing products, and try to stay consistent with traditional standards. And then finally, give your end users plenty of time to test and experiment with a new prototype before it becomes operational. Provide the prototype and the end users native software, provide them with a clean, intuitive interface, give them a way to give you feedback and be responsive whenever they reach out to you. And then finally, provide your end users with training on experimental products when at all possible. It will make the development process go a lot smoother. So I see I'm right at time, so I'll go ahead and stop there. I'll be glad to answer any questions.
Thank you, David. I don't see a question coming up yet. I see in Slack, I see Chris is typing. So one quick question I have for you, David. You talked about the importance of timeliness and with respect to their native software, like NAWIPS and AWIPS. Do you have any forecasters in their open-ended responses talk about how they might be able to get that information faster via web-based platform? Because in my experience, forecasters, obviously it really depends, but you almost see a split where somewhat AWIPS, somewhat web-based.
Absolutely. We actually had several comments about the method of delivery for new products. And the biggest underlying factor, the most common theme that I saw in the responses we received was that if you provide them with your own interface, the interface must be clean enough that they can figure out immediately what they're doing. They don't want to spend a lot of time having to click around and try to, understand how the interface works. They just want to get to the data as quickly as possible and find what they're looking for without a lot of hassle.
Awesome. Thank you, David. And I see a question did pop up for you in Slack, so you can go there. And I'll let
Yes,
Amy.
Well, and I was going to say, they're having a very lively discussion in Slack. They're just demonstrating exactly what to do with Slack. So it's perfect. Go over to Slack and move that discussion, and we will move to the next talk, which is Cindy Lin talking about coding climate injustice.
All right. Thanks, Amy, for the introduction. Thanks so much for being here. My name is Cindy Lin, and I'm a postdoctoral fellow right now at Cornell University. So over the last decade, and especially in the keynote speakers and plenaries we have heard today, we've definitely witnessed a growing interest in responsible and trustworthy AI and data science in the earth and environmental sciences. Yet it's been broadly established that physical and computer science researchers place greater attention to the performance of AI models and less on how end users actually use them. Accordingly, a lot of what makes an AI model usable depends on whether users actually trust these models. And what's considered trustworthy is definitely driven by the needs of end user groups. The European Commission has recently defined trustworthy AI according to 3 principles: that they are lawful, that they are ethical, such as whether they respect privacy or whether they're transparent, and that they're robust as well. And we've also heard from Lynn earlier this morning that there are different kinds of ways in which you can evaluate what's trustworthy. But nonetheless, such frameworks are developed in relation to the legal, political, and social norms of Euro-American countries. How do these principles map onto other regions of the world, especially in countries where public trust in government data and technology have been met with much skepticism? In the following slides, I aim to show how coding climate justice or injustice involves asking just one simple question: whose context matters when designing AI? At the heart of this question is the notion of power. Knowing the context in which certain needs are being prioritized over others can actually inform the design of these technologies and their social implications. I show how focusing on political and socioeconomic context instead of the nominal needs of end users can actually bring into view the dynamics that determine whose needs become primary and in turn direct ethical AI production. As an information scientist trained in social sciences and ethnographic research methods, I've interviewed and shadowed the work of people involved in the design and development of AI and data science for the last 3 years. I've conducted fieldwork mostly in Indonesia and the city of Jakarta, which is the capital of Indonesia, and South Sumatra that you see here dotted beside on red. And I've mostly worked with government and industry, computer engineers and environmental scientists in the 4th most populous country, Indonesia, and one of the most biodiverse regions in the world. During my time in Indonesia, I worked as a research intern in a government engineering agency called BPPT. BPPT collaborated with IBM to develop Indonesia's peatland fire prediction system since 2019. Now, tropical peatland in Indonesia is the world's largest natural carbon storage. So when it dries out and burns, you're basically burning fossil fuels, releasing thousands of years of carbon in just a few months. Hence, tropical peatland have been internationally marked for conservation efforts. But historically, Indonesia's peatlands are where mostly poor smallholder farmers and the world's largest palm oil cultivation are located. So for the last 5 decades, major palm oil businesses have expropriated land from migrant farmers and indigenous communities alike to build both canals and plantations throughout rural Indonesia that you see here on the screen. Now, these canals gradually make peatland susceptible to fire by draining out its wetness, right? These peatlands are usually wet, especially during dry seasons. Palm oil companies, however, are rarely held accountable for building such canals and expropriating land. Furthermore, government research institutions in Indonesia have differing data standards and motivations for producing maps about peatland fires, leading the Indonesian public to mistrust government data as fires have increased in frequency over the years. At the turn of the 21st century, the Indonesian government initiated greater efforts to integrate AI and data science into the management of these fires. It promoted the use of AI and data science as efficient, accurate, and objective in the hope of instilling public trust in government's capacity to manage such large-scale environmental crises. To instill trust in public sector data again, the President Joko Widodo of Indonesia delegated BPPT as an AI innovation center to be built in a private-public partnership with IBM. The President's vision of this partnership was to develop the first prototype of the peatland fire prediction system in just 3 months. As you see on the screen, the peatland fire prediction system was aimed at predicting peatland fires using the groundwater level of peat. Research has shown that the lower the groundwater level of peat, which is decreased due to the draining of peatlands with corporate-owned canals, the more susceptible it is to fire. To derive data of peatland groundwater level, BPPT and IBM scientists and engineers derive such data from peatland water sensors across 142 plant sites in rural Indonesia. The sensors take a single measurement of groundwater level every 10 minutes. While its initial design was more spatial, temporally sensitive, such as the inclusion of rainfall data, the Indonesian government has decided to install sensors that omitted such rainfall data in order to cut costs and scale up the technology across rural Indonesia. Hence, BPPT had to make do with the existing data, most of which cannot fully account for the dynamics of peatland hydrology, as well as the effects of peatland clearing by palm oil corporations. To make things even more difficult for BPPT, ministries who had updated data access to current peatland groundwater level were afraid that BPPT might use this data to show how palm oil corporations had exploited peatland, making the issue of peatland fire prevention political instead of scientific. When one of the IBM data scientists attempted to request the data directly from these ministries, a senior computer engineer in BPPT warned him to never do that again. He reasoned that it might look like BPPT researchers are trying to defy the requests of ministries who refuse to share their data and could be interpreted as an act of defiance. The information needs of BPPT were therefore unfulfilled because of the political context of peatland fires. BPPT of IBM persevered and took this opportunity as a means to show that they could still continue developing fire prevention efforts in a low-cost way. So they used dummy data instead to make their fire prediction model work. Instead of collecting observational data on peatland groundwater level, which would cost too much money and time, the act of collecting data was skipped in favor of producing a peatland fire prediction system quickly and cheaply. Now, this peatland fire prediction system also depended on fire hotspot data from American satellites, such as NOAA's active fire data. To use hotspot data as available for peatland fire prediction system, IBM and BPPT's core data science team follow a simple linear relationship between fires and groundwater level. That the lower the groundwater level, the greater the number of hotspots, or the drier the peat, the greater the risk of fires. To do this, Zhang Li, the senior IBM data scientist, suggested the use of an unsupervised machine learning algorithm called optics. He reasoned, quote, the way to discover patterns in hotspot data is to reduce randomness by clustering them in groups. We cannot just look at individual hotspots, but rather we need to find their concentrations, end quote. Now, optics belong to a series of data mining techniques that most of you might know. So the nearer a point is to another point, the more likely it belongs to the same group of clusters, such as the picture you see here where a group of data points are clustered into 4 groups. With optics, Zhang Li reasoned that the use of optics can help them to derive clusters of varying sizes, means grouping hotspots into small or big clusters, which can be a proxy for indicating big or small fires. This will help them to figure out whether palm oil corporations were indeed responsible for the larger fires, given the assumption that they had the resources to clear land in an extensive way. Just at the very moment that Zhang Li suggested an investigation into palm oil corporations with large clusters, a senior engineer in BPPT interjected. He looked at the clusters that you see here on the right and contrasted it to a map of existing palm oil concessions, saying, quote, "We should not care about the big clusters." Zhang Li quickly added, quote, "Well, I thought that peatland fires are largely the result of corporate palm oil expansion. I read that on the news," end quote. The senior scientist replied, quote, "Look, we shouldn't deal with politics. I don't want to meddle with palm oil corporations because we also take money from them for our research," end quote. Zhang Li understood and said, quote, "We'll look at the small clusters instead." It looked at
Cindy,
first
I'm
that
gonna
Zhang... Yeah.
Cindy, I'm just gonna cut in and tell you you have 10. You're at 10 minutes.
Gotcha. But had made the concession too quickly, given that he knew that large clusters provided more promising results. But as mentioned before, the role of IBM here was to develop the prediction system in a short and quick way. Hence, Zhang Li making the concession to focus only on small clusters came as no surprise. In sum, I want to end with two main points for takeaways. First, I want to draw attention to the difficulty in identifying the need of any end users behind the fire prediction system without first understanding the context in which that need is being influenced by and even silenced. Saying that what one needs is also shaped by the political and socioeconomic context in which data is being produced, distributed, and shared. Consider the context in which BPPT want IBM to not reach out to other ministries for necessary data or to not investigate large clusters. They want them in order to preserve the current political order in Indonesia's governance. Here is where we might consider the role of social scientists like myself in bringing to light the context in which end user needs are being articulated, contested, and even silenced. And last but not least, I've documented how the social impact of the AI system itself is mostly confined to discussion between IBM and BPPT experts, not the farmers, nor even citizens living near peatlands. Scholars in information science have critiqued the narrowing of who gets to define AI ethics as an outcome of what they call technification, where AI ethics becomes a terrain that depends only on the expert authority of computer engineers in order to be considered legitimate. Here, I'm not suggesting that simply adding poor farmers might make the prediction system more inclusive. So where do we go from here? We might consider, in the case of Indonesia, empowering workers to transform the social norms in BPPT, where scientists, instead of being silenced, are incentivized to do slow, purposeful scientific research. In the US, one such movement captures such a spirit, the Tag Won't Build It campaign. Initiated in 2018, Google employees organized against the company's involvement.
Cindy,
yes,
we're gonna have to cut in because you're at time.
All right, sure, yeah. Yeah, I can talk about that during Q&A. It's fine. I'm fine with that. Thank you so much, and I'll be happy to answer any questions.
Yeah, there's some good questions in the chat as well.
Yes, thank you, Cindy, for a really thoughtful presentation. So as we move on, I'm going to apologize, Arjan, because we didn't really figure out how to pronounce your last name. I'm going to guess, and you can correct me. I think it's
Durresi is my name.
Wonderful. That sounds great. Thank you. Go ahead, Arjan.
Okay, let me share my slides. Okay, can you see my slides?
Yes, we can. Thank you.
So my name is Arjan Durresi. I'm a professor of computer science at Indiana University, Purdue University, Indianapolis. So the work I'm presenting today is trustworthy acceptance of AI-based collective management of food, water, energy resources. So this is in the framework of a big project we have with our university, Oregon University. So Meghna Babar-Sebens, she is the PI, and I think she has a poster about the project in general. So this is part of a project funded by USDA and NSF. So basically, it's kind of philosophical questions. How good are computers at making decisions or helping us or thinking? And basically, we can spend our life here and go deep and never come back, even dealing with Gödel's theorems, or we can keep it simple that we don't even know how our intelligence works, or let alone machines. So for this reason, we believe that for the time being, we have to kind of rely on people. So basically, people will be somehow part of the system. So more than just machines, it will be human-machine collaboration. And we have to deal, basic people will be in charge for many reasons. And as I said, the main reason that machines don't have meaning. And because of that, there are many problems if they are let alone. So, and when we deal in collaboration, we have to, even normal collaborations with people, the real kind of glue of collaboration is trust. How much you can trust a partner, collaborator, or person to do certain things. The same applies to machines now, because they are our collaborator. So that's why this Trustworthy AI comes in the picture. And there is a lot of attention related to Trustworthy AI. And the reason is that for AI to become the real deal, has to kind of, now for the time being, it's almost a toy level, has to be trusted to do certain things. And there is not a coincidence that, for example, in European Union, they have kind of ethical guidance, and also very recently, US government accountability office, they released a similar document about artificial intelligence, about accountability. And it's very interesting that industry standardizations are moving here, because finally, whatever we do, our words has to become standard. So basically in the future, like we have standards from everything in industry, we'll have standards about trustworthy AI. So suppose you have an algorithm or a robot or whatever, how trustworthy the system can be kind of certified by some organization. For example, suppose we are dealing with kind of agriculture, most likely USDA has to kind of certify this system. That's why ISO, which is one of the major standardization organizations, they have released kind of first draft. NIST also, which is in US, has released kind of trust and artificial intelligence kind of draft. So, but all of these documents are at the level of high level. So they talk about the need, but the real need here is to develop metrics, concrete metrics and measurements, how to measure this metric, because that's what the standard means. You have some metrics and you are able to measure that. And then, for example, we can bring the example of vaccines. Unfortunately, we have this bad example. We are living through this virus time. For example, FDA certified vaccines, and they had their own standards. Basically, they used their metrics, and finally said this vaccine is accepted. So most likely, AI system have to go through similar process. So basically, in this spirit of creating metrics, we have created some metric for trustworthy acceptance. What it means, and I believe that this acceptance is key, because finally we can have many comments about this AI system. I mean, it's good, bad, whatever, but finally, would the users accept it or not? That's the final deal. So basically, based on this idea, we have developed a metric, and which has two components, the value, and also, as we'll see, kind of the confidence of this value, just like all measurements. And we have played with this metric using some game theory scenarios to illustrate application in this system. So basically, the system itself, as I said, this is kind of work in framework of much larger project, is this interact well. So here's the website. So basically, it's a system, has many things here, AI tools, has optimization, has many models, climate models, SWOT models, and everything. So basically, this system can generate solutions for the users or actors. And solution meaning, let us keep it simple, kind of a group of farmers trying to optimize their use of land, and there are several parameters that they might try to decide what kind of crop to use, what kind of water, what kind of fertilizer, everything. And somehow they have their own land, but also they influence each other. So basically, not only they select solutions, so the system generate kind of pre-optimized solution, and somehow they select them because they have also their own interests. And then other actors in this community, they rate this solution because, yeah, you as a farmer, you might, let's say, try to get maximum profit, but you are not only ruining your soil, but also mine, and so on. So basically, this is the idea. And the system works like this: an actor make decisions, or decision means selecting some of the solutions proposed by the system, and then get gets feedback from the community in terms of trust, which is calculated based on ratings. And for example, if the rating is high, the trust value is high, the actor is happy. If it's low, he might or she might kind of change decision, such because it's kind of balance between whatever they want to reach and the trust from the community. So for this reason, we have used our trust model, which we have proposed several years ago. And here in this figure, kind of explains what it does. So basically, it builds trust, map trust based on some measurements. So basically, we treat trust. This is a simple idea, but kind of it seems to us very powerful. We consider trust as similar to physical measurements, and then after doing that, we apply measurement theory, which is well developed. So basic measurement theory means kind of dealing with errors, because when you do measurements, the real deal is how you deal with errors. And we have applied this. So this is one of the original papers, and applied in many scenarios, kind of stock market, security, and so on. So we are applying here. So it's, as I said, it's similar to measurement theory, uses some statistics, but kind of simple things. And it turns out kind of has worked well so far. So anyway, let us go back to our discussion. As I said, the system generates pre-optimized solutions, and these users somehow select them and get feedback. Now, in this scenario, to keep it simple, we have thought about this because, as I said at the beginning, it's very important to develop standards. And standards, for example, in this case, USDA or similar organizations, similar to FDA, for example, what FDA did with vaccines, they have a group of experts. They looked at the data and then somehow generated a decision to accept it or not. In our case, we have experts. We judge now the output of the system, and we assume that these experts or the community, basically they are expressing the community, let's say, goal, have some goal, for example, to protect the environment or whatever goal might be involved. And then they select the best solutions generated by the system, and they compare how far away or how close are to the goal. And finally, we calculate this distance between the goal and the proposed solutions. And the kind of 1 minus the distance becomes the acceptance. So basically, each expert somehow generates certain acceptance, depending on what the experts think about how good the system is behaving. Based on that parameter, in this case, as I said, could be environment protection, could be any kind of combination of parameters. And finally, we weigh this acceptance with the trust of the experts. In this case, to keep it simple, the expert, we assume that USDA had hired top experts and somehow the trust is high, but this could be applied in other scenarios where the trust kind of is not high, normal users, and as I said, can really help to reach some joint decision. So a solution is nothing else than some kind of basic parameters for users can deal with, like groundwater, surface water, crop choice, fertilizer choice, and so on. So these are parameters of the solution, and they choose between solutions which are, as I said, pre-optimized initially by the system. So then, as I said, we calculate not only the value of acceptance, but we calculate also the confidence, which is basically somehow based on the error. So basically on the error of those calculations, the variance, we calculate the confidence. And this is extremely important because we have seen also in other fields. So if the confidence is low, basically the measurements is worthless. Like even any physical measurements, if somehow the confidence, the error is high, the measurements is worthless. On top of that,
I'm going to interrupt and let you know you're at 10 minutes, so you have about a minute to wrap up. Thank you.
Okay. So basically, we can test the system in many points, not only in one. So basically, we can kind of summarize and have many points and basically average this acceptance. And then we have simulated our system with 200 fields. We somehow created 3 systems, and we have so-called expert. Basically, this is game theory, so simulation based. And for example, here are the results. For example, the 3 systems, they are judged by the experts, 3 experts. It turns out A, B, C. The first system, the blue system, looks the best, and this is the orange system, the second, and the yellow system. And these are in different fields, different points, and then this is summarizing all of them. So basically, the end result would be like this. So if USDA was testing this system, the blue system is kind of close to 9, the orange close to 8, and yellow below. So basically, suppose USDA might have a kind of threshold saying you have to reach 0.8, only these two systems would be accepted and by the USDA in that case. Again, these are the numbers for that. And this is the conclusion. So basically, we developed this metric. And the interesting thing is that metric can be used for many other things. And we are working on that. So that's my presentation, and I will be happy to answer questions.
You'll need to answer your questions in Slack, I think, because we're out of time.
Yep.
Brian, can you share your screen? The next speaker is Brian Hugh on Explainable AI from fish classification to open source toolkits.
Can you hear me now?
Yes, we can.
Yes.
Okay, cool. Hi, my name is Brian Hugh. I'm a senior R&D engineer at Kitware, and today I'd like to talk to you about an open source explainable AI toolkit that we've been working on and have applied to several use cases within NOAA. And this is joint work with others at Kitware, and as well as with collaborators from the Southeast and Southwest Fisheries Science Centers. So first, what is Kitware? We're a small open source software R&D company. We have expertise in the areas of computer vision, medical computing, scientific computing, and data analytics. And a lot of our work comes from government contracts, including work on several projects with NOAA, with a smaller side of our business, which does commercial work. So the outline of my talk today will be first to cover briefly what is explainable AI or XAI, introduce some of Kitware's open source tools, including Beyame and XAI TK saliency, show how we've applied these tools for these two use cases of fish classification and penguin behavior classification, and then finally to introduce this XAI toolkit, which we are working on. Okay, so nowadays, as many of you know, we have access to large amounts of data, and this data can be used to train complex machine learning algorithms. So in this case here, we can train up a model which does image classification. So it could take in an image of a cat here and make a confident prediction that this is a cat with maybe a probability of 93%. One of the issues is that when an end user comes to actually use this model, he may have a hard time understanding why the model predicts that this is a cat or not. And so the idea is that explainable AI or XAI provides tools and resources to help users better understand and appropriately trust these machine learning algorithms. So again, going back to the case of image classification, given the same image of a cat, the model might predict that this is a cat, but it also provides an explanation of why it thinks it is a cat. So for example, it might say it has fur, whiskers, and claws, or it might have this feature of these pointy ears here. And the hope is that by providing this explanation, a user who is interacting with this machine learning algorithm has a better understanding of why the model makes a particular prediction and can also appropriately trust the model under certain circumstances. And if you're interested to learn more about this research, there was a DARPA XAI program which sponsored a lot of this research. And you can find that link here. XAI can operate at multiple levels. So here I've shown a standard AI ML pipeline, which typically involves data, building some AI ML system, and there's usually an end user who is going to be using this system. And so XAI can operate on the data itself as a form of pre-processing. So this might help a user visualize or explore their data. XAI might operate on the AI ML system itself. So one example might be to create a more inherently interpretable model. And oftentimes you already have a model which is already built and trained. And so you can use XAI as a post hoc type tool to try to understand what the model has actually learned. And then obviously XAI can be used as a combination of all of these different levels. And for the talk today, I'll focus mainly on XAI as a post-hoc method, but I will say that the toolkit that we're building seeks to incorporate tools from each of these different levels of integration. And first, before diving into the actual use cases, I'll introduce two of the tools that we used. So the first is this Viame toolkit, which is a video and image analytics toolkit, which is built for marine environments. It's designed to be run by people with no programming background, so it's very easy to use. It's fully open source. If you're interested to learn more, the toolkit is hosted at viametoolkit.org. And accompanying the toolkit is also a public annotation archive and model training server, which is available at viame.kitware.com. And if you're interested to learn more about this tool, we have a session tomorrow afternoon that describes more about this Viame toolkit. The second tool that we used is this package called XAI TK Saliency, which is part of the larger open source explainable AI toolkit. Here, saliency maps are a form of visual explanation, which reveals what an algorithm pays attention to during its prediction process. And so we have support for different image understanding tasks, including classification, image similarity, and object detection. We tried to design the framework to be very modular and extendable. And we also have several notebooks to showcase how to use the toolkit. And if you're interested to learn more, we have a GitHub repository at the link below. Okay, so first, I'll turn our attention to the problem of fish classification. And to do this, we partnered with people at the Southeast Fisheries. This is part of the CMAP program. So the idea is to monitor the health and movement of fish in the Southeast area. And to do this, what they do is they put down different camera arrays in these different locations. And so an example camera array is here. And these cameras generate large amounts of data. And so it's not feasible to ask someone to actually sift through all that data. So automated techniques employing AI are needed to actually detect fish, track fish, and classify the fish. And so the goal of this effort is essentially to build a publicly available data set, which can be used to train these models, but then also to make models that can eventually be deployed in the Southeast area for the task of fish detection and identification. And this is work from Jack Pryor and Matthew Campbell. And so here we focused on the particular subtask of fish classification. So it's important to note that this step comes after detection and tracking. So the whole pipeline involves detection, tracking, and classification. But here, for the purposes of this talk, I'm just focusing on the classification part. So here we use the ResNext model, which is pre-trained on the natural images and then fine-tuned on these fish images. Our full data set is about 150,000 images and contains over 130 different fish species. Some of those example images are shown below here. And on a held out data set, this model achieved an accuracy of around 83%. And so here, what we did was we tried to use saliency as a way to better understand the model's predictions. So here we focused on the class of red snapper, which is one of the most prevalent classes in the data set. What we found is that when the image of the fish is relatively close and the eye is visible, saliency often focuses on the eye of the fish, which suggests that that's a critical image feature, which is used by the model in its prediction. And interestingly, when the eye is not visible, for example, when it's covered by this bar, the model tends to use much more diffuse features like parts of the body of the fish. And so we're interested to extend this analysis to better understand model failures. So when the model makes an incorrect prediction, what does the saliency show? And similarly, what does the saliency focus on for other species of fish? Okay, next, I want to talk very briefly about some of the other work that we've been doing with the Southwest Fisheries Science Center. They're interested in studying predator-prey relationships in the Southern Ocean. And so what they do is they attach these cameras to the penguins and they record video. And these videos can be helpful for analyzing penguin dive behavior, as well as different penguin prey interactions. And again, similarly, because a lot of data is being generated, having automated AI techniques to help analyze this data is critical. And so this is work, again, from Victoria Hermanson, Jefferson Hinkey, and George Cutter. So what we did is we worked with them to create a full frame classification model. Again, we use this ResNext 101 model. We have a data set of about 1,600 images that have been labeled into these 5 different classes, which are shown below. So one is open water, one is when the penguin breaks the surface of the water. There's a class called blasted, which is just a washed out image, which is usually discarded. And then there are images that contain either penguins or krill. And after training on this data set, the final accuracy of the model on the held out portion of the data set was around 96%. And so here what we did was we tried to see if we could use saliency to help localize krill in images that contain krill. And so again, here these are images where the model correctly predicted krill. And in the first row, we see when there are krill in the images, saliency does tend to focus on them, but the krill have to be relatively large and have high contrast. And in contrast, when there are either a lot of krill in the image or the krill are very low contrast, there are failure modes where the saliency doesn't seem to be well localized. And so we're exploring whether we can build off this work, and in general, whether we can use saliency as a useful tool to help debug the model and improve the model in future iterations. Okay, and finally, I would like to introduce the Explainable AI Toolkit, or the XAI-TK. It's designed to be a single central publicly accessible location to find different XAI tools and resources. And so this includes things like software, models, different data sets for explainability research, reports or guidance about best practice on how to apply XAI to different use cases, demos of the different capabilities that are present, as well as publications about the latest research in XAI. And this is, again,
Hey, Brian, I'm going to cut in, just tell you that you're at 10 minutes. So you get about a minute.
Yeah, this is a follow-on effort that was supported by the DARPA XAI program. And as I mentioned, we also want to create software frameworks. So the XAI-TK saliency package is one example of where we've been able to integrate different saliency algorithms. And alongside this, we want to design a guide to allow new users to be able to navigate this toolkit and find the right tool resource for their needs. And again, this is going to be fully open source and hopefully a valuable resource to NOAA and other partners as well. And finally, this is the last slide. We have a website on the toolkit. You can find it at the link xaitk.org. It's live. This is the landing page of the website. It has links to the different capabilities and a brief history of how the toolkit came about. And then inside the toolkit, you'll find these different pages which highlight different contributions. So in this case, this is one for a question answering system where you have the pointers to different resources, whether they're code or papers on the left. And there's also important metadata, which is stored with each contribution, including the intended use case of this tool, as well as potential limitations. And with that, take any questions. And thank you everyone for your time and attention.
I think we are out of time.
Brian.
Oh, go ahead, Jolie. Sorry.
That's what I was just going to say, Amy. We're on the same page. So I see some questions popping up in Slack for you, Brian. So I would go look over there and start responding to them. And then we'll move to our last presentation so that we can have a few minutes at the end for discussion. So last, but certainly not least, we have Courtney Bowman, who's going to be talking about responsible AI and ethical framework.
Hi, everyone. It's a pleasure to present to you. My name is Courtney Bowman. I'm the Global Director of Privacy and Civil Liberties at Palantir Technologies, and I'm going to be motivating and presenting a framework for ethical and responsible AI. I want to start by addressing the motivation of why ethical AI matters. Like all rapidly developing technologies, the law and regulation tends to trail the state of the art. This means that determining how novel technologies should be used is not just a question of what those technologies can do as a practical matter, or what they're permitted to enable as a strict regulatory matter. It's also a question of the ethical considerations that are likely to shape the landscape of permissible use in the present and the future. Now, of course, NOAA and its surrounding scientific community carries a long history of using advanced data analytics technologies to perform its core functions. So in many respects, this community's approach to AI and AI externalities will hopefully already be baked in some of the maturity of that deep background. But as new approaches to AI and ML become more readily available and use cases become more expansive, aided in part by advances in computing power, expanded data source availability, and modeling technique developments, the complex and evolving challenges that are emerging may strain the normative boundaries of how NOAA and its community of researchers should consider AI and its ethical ramifications. This will be the case even if the focus of data in the environmental sciences is not primarily on personal information, with explicit ties to people as ethical subjects with formal rights and entitlements. Now, we've all followed AI ethics discussions as they play out in a multitude of other domains, where, for example, algorithms intersect with personal data and application of AI carries immediate and direct impacts on lives. But in fact, responsible and ethical AI use also touches on the seemingly impersonal sphere of climate, weather, oceans, and coasts. Now, why is this? Putting aside any questions of ecological or ethical obligations to the environment as such, we must recognize that the environmental sciences and their methods of studying the world around us have direct, or rather indirect, but deeply consequential impacts on our lives. Advanced analytics, modeling tools, and more general AI technologies that are leveraged in environmental and earth sciences can subtly but significantly carry through to real-life human consequences in ways that may already be familiar to you as practitioners and researchers. To name just a few examples, think of forecasts that prepare communities for weather events and climate changes, mapping exercises that display coastal communities under changing weather and water management scenarios, models that predict environmental precursors to disease outbreaks. All of these techniques and undertakings have communities and human lives and tangible impacts as their endpoints, and therefore they necessitate a consideration of their corresponding ethical, responsible uses to ensure defensible outputs. So more concretely, a baseline starting point for responsible and ethical AI approaches begins with a recognition of what AI can and cannot do. These constraints are both practical in the sense of what is technically possible and normative in the sense of what is socially, culturally, and morally permissible. Let me start with the practical side. It begins with an awareness of an understanding and appreciation of AI's practical limits and categorical constraints. What is the technology actually capable of doing? Foremost, let's consider that computational intelligence is not intelligence as such. Labeling a technology intelligence is laden with implications and assumptions that are dangerous if left unacknowledged or misunderstood. And contrary to so much media and developer hype, AI is not intelligence in anything like the senses we think of with human cognition, which is beyond pure rational inquiry and is inextricably laden with moral, cultural, and social implications. It's more helpful and accurate to think of AI in terms of what it currently amounts to technically, as a set of tools, computational capabilities, statistical pattern matching, expert rule systems for solving narrow problems in specific contexts to assist subject matter experts in processing data to address real-world challenges. A practical grounding of AI also motivates the elevation of empirical results over pure research and laboratory experiments, often involving unrealistic toy models. Now, this is not meant to impugn the value of research and development, but rather to put it in its appropriate place. For AI, or any technical tools for that matter, to prove its mettle, it must produce demonstrably useful, reliable, and sound results in complex, messy, often ambiguous settings. Think, for example, of natural language processing for sentiment analysis. It may be a tempting tool for understanding public reactions to weather warnings or messaging of climate change impact. But in practice, however, this often proves to be a noisy and practical tool for interpreting and making sense of expressions of thought, ideas, and reactions that are often deeply nuanced and conveyed with equivocal modes of speech. So let's next turn to the set of considerations that guide what the technology should be applied to do, that is, its normative constraints. This starts with a value-driven orientation to help direct where technology uses will reinforce core commitments. NOAA, for example, is an agency that exists to serve the common good through a science-driven understanding of climate, weather, oceans, and coastlines. Informing the public about the environment around them, how it is today and how it is likely to change tomorrow, requires several value-oriented assumptions, including, but by no means limited to, trust and integrity in scientific methodologies and frameworks, and especially those in environmental sciences, a sober assessment of the state of the natural world and how its changes will impact societies, and a conviction for how and why scientific conclusions should impact the common good through various initiatives and means, such as enriching public discourse and contributing to policy debates. Then there are aspects of cultural awareness, which were addressed earlier in this panel, to consider how to help determine when and how technology applications can best align with the interests of impacted communities. Environmental sciences may have objectivity at their core, but how the sciences are applied and how derivative technologies and their outputs are received can be conditioned on many subjective factors. AI applied responsibly to environmental modeling will increasingly veer into social and cultural issues and challenges, such as questions of bias and equity. For example, will models of climate change equitably produce impact projections on disadvantaged coastal communities versus more affluent communities, where perhaps the underlying data is more reliably captured? Finally, what may be technically practical is not always virtuous or ethically defensible. In other words, just because AI technology might be viable ways to support an environmental initiative or outcome, that does not necessarily mean that we should use AI for a given application or even pursue the outcome in the first place. Now, examples of this abound outside of the environmental sciences. For example, facial recognition that's been used to infer sexuality or violent tendencies. Directly analogous examples may be harder to identify in the environmental sciences, but one can readily imagine adjacent types of ethical questions. For example, do AI modeling computations generate an energy and resource footprint across their full supply chain that exceeds their potential value to inform climate change policies? Now, ultimately, it's the more grounded approach to knowing AI's limits that helps to provide technological tools that are more likely to be reliable, durable, and effective. So beyond those baseline considerations, we can crystallize some guiding principles for the application of AI tools for environmental science. The first being, don't solve problems that shouldn't be solved. Problem selection should serve an essential threshold consideration in any AI system undertaking. And it begins with a serious examination of the practical and normative limitations of AI previously discussed. Problems for which AI is simply not up to the task or otherwise inappropriate are better treated through other means, not always technology-based. Secondly, collect and select data responsibly. Predicated on the assumption of a valid and defensible AI application, the second step is a responsible AI assessment framework relates to the collection and selection of data that may be used to deploy AI algorithms. Acknowledge that context matters and is essential to determining whether specific types of information should be used in AI projects. For example, does aerial imagery of coastal regions present unintended surveillance risks if collected at high resolution, or can the imagery be obfuscated to limit potential misuse? Next, methodically assess and address sample bias. Any credible AI effort must grapple with the garbage in, garbage out problem. Stated differently, no matter how rigorous the design of an AI application is, if the data used for training and development is irredeemably flawed, the system output will almost certainly be compromised as well. This issue is even more pronounced where training data reflects systematic or other institutionalized forms of bias. In the environmental sciences, for example, we might think about ways that more affluent societies may create more voluminous and higher quality data, training data that is disproportionately skewed models to more accurate or more favorable assessments on their local shores, while disadvantaging the same models for more vulnerable societies. At a minimum, where such biases exist, they should be studied and understood and appropriately documented. Next, consider carefully monitoring outcomes, understanding equity assessment trade-offs. Beyond addressing feature selection and sample bias, which may contribute to disproportionate or skewed applications in the mechanics of a given AI system, a responsible approach to AI must also deal with the risks associated with disproportionate impacts in that system's empirical outcomes. Evaluating how AI outcomes may be skewed across different population segments, for example, can assist in further algorithmic refinements aimed at optimizing outcomes on appropriate evaluation parameters. Then consider ensuring audibility, explainability, and interpretability, which has been addressed in earlier presentations. Responsible AI use must enforce accountability through a number of discrete measures and techniques. Auditing in the form of in-process system records and audit logs should be employed to ensure that data processing events contribute to specific outcomes, and in later stages can be interrogated and documented as needed. AI models must also be explainable to various relevant stakeholders, subject to both regulatory and normative considerations. Finally, interpretations of models should provide a clear assessment of trade-offs made and attendant consequences of choosing certain optimization parameters over others.
Courtney, I'm going to interrupt and let you know you're at 10 minutes, so you have about a minute to wrap up.
Got it. Wherever possible, keep humans in the loop. And generally speaking, AI is both most effective and most defensible when employed to assist human decision-making rather than replacing it. Finally, promote multi-stakeholder engagement. It's important to consider incorporating broad stakeholder involvement in building, deploying, and overseeing AI applications, which is especially true where environmental sciences draw upon outputs of AI systems to inform far-reaching policy discussions. So to wrap up and put it all of this together, a principled approach to responsible and ethical AI in the environmental sciences continues to regard human lives and human impact as a central consideration, even when the data and the models are focused elsewhere in the natural world. But adopting principles is one thing, and implementing them is another. Responsible AI depends on the transposition of these ideas into institutional guidelines and procedures that can be used on a daily basis. And beyond discussions of fairness and bias mitigation, it also requires reinforcement through data science and technological means that address the full data and model development and deployment cycle. That's a full topic for another day, but let it suffice to remark that having the right tools, procedures, and institutional governance practices in place is just as essential to the viability of artificial intelligence techniques in the environmental sciences as is firmly grounded understanding of the practical and normative limits of what AI can and cannot do. Thank you.
Thank you, Courtney. So I think we have time for one question for Courtney, and then we'll open it up. And there is a question from Emma Ibertapov in Slack. Courtney, she says, I always struggle with this question. How can you make sure your data do not have bias? We can check for obvious things, but we can't check for everything. What are your thoughts on that?
Well, so first off, it's worth considering whether the bias that you might identify in your data is good bias or bad bias. Bias in itself is not necessarily bad. It depends on the type of implementation and context. And we can't always exhaustively detect every form of bias, but the critical point is that we acknowledge some of the structural considerations that might figure into our field, as well as understanding all the statistical modes that bias may manifest, and do our best, our due diligence to address those bias considerations and document. The documentation is a critical component. Document how we've carried out those evaluations and how we've sought to mitigate the bias that we've identified.
If you can stop sharing your screen, we'll go to doing questions from everybody, which will include you, but.
I will try to unshare my screen.
And we were going to start with, for the cross-cutting question that sort of cuts across lots of people, and there's been a very active discussion in the Slack on this as well. But how do we, this is from Ann Bostrom, how do developers think about the needs for speed and how they trade off between trustworthiness and ethical co-production? Do any of the presenters want to jump in?
I think at some point, trustworthiness has to come first. It's like a medication. Do we want a medication which is safe? And then it's kind of effective. The first thing for example, for the vaccines, they looked first if the vaccines can harm. Then they looked how good they are to deal with the virus. I think finally, this would be the view of AI or as any other tool. The first thing they should not harm.
I'd also add that the value of speed is really context dependent and should be considered with reference to the risk that you're trying to deal with. Acting more quickly in an exigent circumstance may make more sense, but you also want to put boundaries on the application. And there may be a window through which you're willing to act quickly, after which you do more involved evaluations. But constantly you have to make those risk assessments and be mindful of the context and how that changes over time.
Anyone else want to comment on that? Otherwise, I think we have a couple other cross-cutting questions here.
You've got a really good one from Chris in the Slack.
Yep. So let's see if Chris says, panel related to Emma's question, revisiting a topic from plenary 2, how can we regain trust with stakeholders in the public if we stumble? hindsight's 2020. Obviously, being responsible in development is key, but something will surface that looks obvious in hindsight. So really, how do we regain trust with stakeholders in public if we stumble?
I would say I think that's a really difficult question. I think what people alluded to, having proper practices in place to ensure, transparent, responsible AI development is important. And essentially learning from, just like we learn from any kind of disaster or thing, being able to learn from these cases where we failed and improve in future iterations.
I'm gonna throw that question a little bit at David too. David, I know your camera's not on, but I'm assuming you're there. The for SPC, in the HWT, sometimes things in the HWT fail. So how do in your observations of the forecasters and looking at those methods, how do they regain trust if a method fails?
Right. So this is one of the things that we're really kind of digging into with some of my research and the stuff we do in the HWT. Honestly, the best thing that we're able to do at the moment, according to the forecasters themselves, is to simply explain why the product failed the way it did. If it doesn't perform the way that it's expected to, the more information we can provide about, why did it do that? Is it going to keep doing that? Are we doing something to fix it? The more information we can provide our end users, the better. Because, and especially the high level end users like the SPC forecasters, they don't just want us to, they don't just want to blindly trust us to hand them a product and say, okay, it works now. They want to know, a lot of details about it. And the more details we can provide them, the more trust they will have in it, even if it doesn't always perform exactly as expected.
I think just to add to what you said, David, I think your point about providing kind of case studies in conjunction with bulk statistics, and I've had forecasters say not just case studies of when it worked, but when it also didn't work. So it really is being transparent upfront about some of those failures, and then to the extent that you can convey what those failure modes are is important. I would also offer, and we're touching on it in a space that I only know just enough to be dangerous about, but to be able to draw on principles of crisis communication with whatever the context of the topic is, and being able to kind of very quickly own up to it. Depends on what we mean by stumbling. So, that's a question that's embedded in your question, Chris. But, being transparent, being really quick to identify and address and be honest about those shortcomings or problems or stumbles in some way is really an important set of lessons out of crisis communication research that's been done. Any other thoughts on that question?
Yeah, one thing I have to add, I had a quote in my slide saying that before using the models, we have to be kind of aware of the potential errors of the model itself. So basically, if the errors are there, and could be prediction, you cannot be done with existing technology, and you have to make that clear. And it's not just a question to make a prediction, but if the error is too big, basically, it's not a prediction.
I like also that all of the responses have focused on it being a small failure. I kind of wonder what different. We jump into something like Tesla, and Tesla, people have jumped into, hey, it's autonomous, let's just drive it, and then they die. That's a different failure mode than we got the hurricane track off by a little bit, although there's still major implications to that. I wonder how the different failure modes for environmental science, weather and climate might affect our trust as well. If anybody wants to tackle that. Sorry, is that too hard?
But probably, as much as I know, I'm not an expert on this, but climate probably is one of the good examples. I mean, we have done great in climate prediction compared with years ago. Now, other things like Tesla, you mentioned, they are still kind of new kids, and they have to grow up and go through this process of testing from a trustworthy point of view. And just, it's not a question to have this self-driving car just for fun, but I mean, to put that car in real conditions, and really it's far, far away from good deployment.
Courtney, you unmuted. Did you want to answer too?
Yeah, I mean, I think there's different scales of failure to consider. Self-driving cars, the immediate consequences are very apparent, whereas with climate sciences, the consequences can be compounded over generations. And so, if anything, that escalates the severity of failure and motivates a deeper regard for the importance of getting things right, and where you don't get things right, acknowledging those failures and striving to do better the next time.
I think those are really good.
I would also add, like, across the government, there are agencies which are working on standardizing measurement and evaluation of AI. So like places like NIST developing standards for how to like measure and quantify AI systems, and then places like the Joint AI Center to develop kind of government-wide frameworks for ethical and responsible AI development. So there's efforts, maybe not in climate science particularly, but there is, I guess, increased traction and interest across other government entities in this area.
That could be as well. Sorry, sorry.
Go. You go.
But I think, sort of coming back to the last point that I mentioned, the discussion around AI ethics, at least in the environmental sciences, still seem to be kind of limited to the experts, right? I think it's mainly climate and environmental sciences is a domain in which one has to be trained in, right? It's not something that is everyone could have a say in that. But I do think that, coming back to one of the questions just now, the people who do get impacted by climate change are mostly impoverished communities. So I think in part, the questions also to us, as what I think David mentioned, like who do we bring into the table when we decide, this technology should be implemented, because climate change has affected a lot of communities in a very palpable way. Maybe not us in a very because we are not in some of the more impoverished communities, I don't know, or we might be, but the point here is that we are still fairly privileged, right? So I think maybe some of the discussion around how to include some of these communities who are being disenfranchised might be important.
Thing also that came to mind based on your work, Cindy, relative to this question, and forgive me if you said this, is I find it, I'm not very good at monitoring all the Slack and like everything at the same time. I'm not quite as deft at this, but I think your context specific work with users also helps us understand, what do they consider failures? What kinds of failures are important to them? Are there things that are inadequacies that maybe aren't thought about by the developers, but that actually are by the users, and vice versa? So that context specific work with them in this context of failures and thinking about them seems to me as though it's very important too.
You have our next question out of all of the questions that are going on. There's a lot of discussion going on. It's very good. I thought you were cutting in with the next one.
I was going to, but I was waiting for you, Amy. I thought about I could ask DJ's question here.
Okay.
So David John Gagne asks, he directed this at Courtney, but I think that this really can be panel wide. Courtney, some of the issues brought up in your talk are not unique to AI systems. How much of the trustworthy AI guidelines should we be applying to auditing / regulating our numerical weather prediction models, climate and observational systems?
Sorry, I was muted. I think it's an excellent question, a very astute one. It's one of the points that I was trying to draw out in grounding AI, not as a magical panacea, but as something more like a tool that fits into broader information systems and enterprises. So yes, most of these principles actually apply much more broadly across the full stack and data pipelines of other types of information systems, and should be taken into account, not just where AI is the primary technological mode of interacting with data, but anywhere where we're dealing with information systems, there's some significant component of those principles that really will come to bear.
Great. Anybody else want to comment on that?
If not, I think we'll let Chris give the final announcement. Chris, do you want to come in?
Sure. Well, thanks everyone for a great panel discussion, and also a reminder that the discussion can continue on this topic in the Slack. That's why we set up these individual channels, so please continue to do that. Just from the planning side, we want you to all know that 4 p.m. Mountain Time, we'll be going to Kiko Chat for our first poster session. And the link to Kiko Chat is in the chat. And you'll also see a notification in Slack if you lose it once we end this session.
And we thank you all for staying, and that was a great session. We look forward to seeing you in the next sessions. And don't forget to go to the posters. I will say that because, you know, some of the posters in some of our virtual conferences, a lot of them are students, and I've had students who've come out of the poster sessions in these virtual conferences and said no one came, very sadly. So please go to the posters and go interact with them. Students or not, interact with any of them.
Thank you, everyone, for these wonderful presentations this afternoon. Very thought-provoking.